the CERIAS Security Seminar Series for January 28th. It's my pleasure to introduce Ryan Riley, who will be talking about memory architecture to prevent code injection. This is a good chance for you to see exactly what you become with a Purdue education in information security. Ryan has been here for his bachelor's degree, got his master's a couple years ago, and will be completing his PhD this year. So, welcome to Ryan.
Thanks. So yeah, like Dr. Clifton said, I've been here for my 9th year at Purdue. I'm quite anxious to graduate and leave. But I am a PhD candidate in computer science, and August looks like the time frame for when I'll graduate. And what I get to talk to you about today is actually kind of the core of my dissertation work. So I'm excited to be able to do that. Now the title of today's talk is an alternate memory architecture for code injection prevention. So it's kind of a big title with lots of terms in it, and we'll hopefully define those as we go on through. But just from the title itself, you can kind of look at it and realize that I'm talking about the code injection problem, and I want to be able to prevent it, and the angle that I'm looking at is from the memory architecture approach, so the architecture of the computer that these programs are running on. So before we get going too deeply, I want to discuss what is code injection. For those of you who aren't familiar with it, or for those of you that are, you can get an idea of the definition I'm using for the rest of this talk. So I want to kind of describe it by illustrating it with an example. Imagine we have a running process, and it has instructions, and it has data. Now, as the process runs, the instruction pointer just slowly moves through the instructions at a normal pace, executing the instructions as you would expect a program to. Now, let's imagine that we have an attacker somewhere, and that our program actually has a flaw, some sort of error in it, that will allow him to both add arbitrary information to the program's data, and at the same time move that instruction pointer to wherever he wants. So the first step for him is to add his malicious code onto the end of the data section. And now that he has his code there, his next step is to simply move the instruction pointer to point to it. So if he can actually pull this off, then I call this a code injection attack. So it's where he adds malicious code into a running process and then gets it to execute. So at this point, the attacker has managed to have arbitrary code executed at the privilege level of the process that had the flaw. So how is code injection used? If we know that code injection is the problem I'm tackling, what does it look like in the real world? So usually you combine it with some sort of memory error. And the memory error is what allows the attacker to either add his code and hijack the instruction pointer, or just hijack the instruction pointer. So there's a number of these that are out there and available. For examples are things like a stack overflow, format string vulnerability, a heap overflow, or a double free. So these are terms you may have heard in the news or on vulnerability reports. But if you take one of these and you combine it with code injection as your technique, then what you get is some sort of valid attack. An attacker may have the goal of spawning a shell at the privilege level of the process that he compromises, or it may be some sort of self-propagating worm attack. Those tend to exploit code injection. Or it may be, in the case of compromising an operating system kernel, rootkit installation. So why is this a problem? And what I mean by this question is, what about computers makes them vulnerable to code injection? So many computers are actually inherently vulnerable to code injection because of the memory architecture that they use underneath. That architecture is called a von Neumann architecture. And in a von Neumann architecture, there's no distinction between code and data from the processor's perspective. So the processor can write to a given memory address as if it's data, and it can fetch from it later as if it's instructions, and the architecture makes no distinguishment. So that means that your malicious code could come from data sources. They could come from files, they could come from the network, it could come from a user interacting with the system. So any of those could be used to add malicious code to a system. So a von Neumann architecture simplified kind of looks like this. So we have a physical memory space, just one physical memory space, and it has both instructions and data scattered throughout it, and the processor issues all of his instruction fetches or his data reads and writes. Any memory access just goes to that physical memory space. So there's no distinguishment, like I said, between code and data. Now, one big flaw in this architecture is, like I was talking about, that it's vulnerable to code injection because of the fact that the processor sees everything the same. But there are other advantages to it. One of the major ones being that it has a huge install base. So most commodity computers that you're going to use, like your desktop, your laptop, the server that your favorite website runs on, all of those are going to use a machine that has a von Neumann memory architecture. But not all architectures are von Neumann, and they're not all inherently vulnerable to code injection. So another architecture that's not vulnerable is called a Harvard memory architecture. So in a Harvard memory architecture, we have two separate memory spaces, physically distinct, One's the instruction memory and one's the data memory. You're actually probably already familiar with this, you just don't know it. Most embedded devices, or at least a lot of them, will have this Harvard architecture. So you'll write your code to a little EEPROM chip, and you have a little bit of RAM there for processing data, but the two aren't mixed. So when the processor issues an instruction fetch, it goes to some sort of code memory, and when the processor issues a data read or write, it goes to a data memory instead. So the processor actually can't address the data memory for an instruction fetch, and it can't read or write from the instruction memory. It's simply not a feature available on this architecture. So given that, the Harvard architecture is actually immune to code injection because it doesn't have the necessary features required to support it. So what if we could have an architecture that has the wide install base of von Neumann and the immunity of Harvard? And that's kind of the core of my dissertation work, is saying what if we could put together an architecture that could have the best of both worlds? So what I'm proposing is a new architecture that has the immunity of Harvard, but is constructed on top of a von Neumann architecture. And it looks something like this. We still have one physical memory space, but we put restrictions in place to ensure that the processor can only access a certain portion of physical memory when it's doing instruction fetches, and has to access a different portion of physical memory for data reads and writes. So the instruction fetches can't go to the data section, and the reads and writes can't go to the instruction section. That's kind of the ultimate goal of our architecture. So on this new architecture, what would a code injection attack look like? So we have a normal process layout that looks something like this, with our instructions and our stack and our heap. And now imagine that if we instead split it up, and this would all be in one physical memory, but we're going to keep it split for the illustration purposes, so that all the instructions are in one portion of memory and all the data is in another. So if an attacker manages to compromise the running program because it has a flaw and take his attack code, when he goes to inject it, the processor will address the data portion of memory and it'll write his attack code there, because that's where all data reads and writes go. When he later hijacks that instruction pointer and gets it to point to the added malicious code, well, the processor will address the instruction space of memory, and it'll do its instruction fetch and find that his code isn't there. And if his code's not there, then his attack fails. So if we can have a system that operates like this, code injection simply won't be a possibility. So I've made some important claims about this particular architecture. One is that it can be constructed on top of the von Neumann architecture. And that's what I need to prove in the rest of this talk. And I'm going to do that by describing how it can be built at both the user level and the kernel level to prevent code injection attacks. So first is at the user level. So my goal here is to take an unmodified program that may have existing flaws that would allow this attack to take place and run it in such a way that it will be on top of this architecture. I don't want to require any hardware changes, so I want to be able to do this on a completely existing machine, and I want to enforce it in such a way that the currently running application can't circumvent this architecture, which means that I have to enforce these rules at a level more privileged than the application itself. So in the case here, the best place to do that is in the operating system. The operating system is more privileged than the application, so he'll be able to enforce these rules. So what's our problem space? If we're dealing with code injection at the user level, what do these sorts of attacks look like? Well, they actually look like what I've already described to you, where the attacker basically hijacks program flow, runs his own malicious code of some sort, and he uses that to either gain new privileges to a system he didn't already have privileges on, or to elevate his privileges in some way on a system he already does. So as an example, consider a running system that has like a mail daemon on it, and that mail daemon has a bug in it, and the attacker remotely connects to it, exploits that bug to add his own code and get it to execute and spawn off like a root shell. Now, our goal is to be able to run that vulnerable send-mail system as is without any changes and be able to prevent that attack from happening. So there's a lot of previous work actually on dealing with code injection at the user level. One approach is language level approaches, so dealing with things like Java or C#, and their goal is to remove all of those memory errors that attackers tend to use. And they actually do it quite effectively. The only main downside actually to language level approaches is that they're not widely adopted enough. So there's still a significant amount of existing and even new software being written in languages that aren't safe in this way, languages like C, and so these approaches don't work to help prevent those attacks. Another type of approach is a compiler-based approach, things like StatGuard or ProPolice, and basically with these sorts of approaches, the goal is to take one particular memory error and architect the compiler in such a way that it will remove that flaw, or at least find them and prevent them from being exploited. Now the trouble with this is that if you have a new sort of technique or a new type of memory error, well then your results will fall apart, and certain of the techniques that the compilers use to break certain memory errors can be circumvented. So other approaches are randomization approaches, things like address space layout randomization, which is where you move around the stack and the heap and things like that, so that once the attacker adds his malicious code, he has no idea where it is. And if he doesn't know where it is, then he doesn't know where to point the instruction pointer. But things like this are also circumventable, and they also tend to have low entropy, so that an attacker might be able to guess. So for example, a few years ago, there was this exploit for Windows to do the animated cursors. It was a really strange little exploit. But after that came out, I went on Google, searched for the exploits, and the very first one that popped up said, vulnerability exploit, Microsoft ANI cursor bypasses address space layout randomization. So what that tells me is that this is possible to get around, so it might not be a good fix. Instruction set randomization is another randomization approach, and the thought here is just encrypt all the code, and then the attacker doesn't know the key, so he can't create new code. The problem is you have to decrypt all that code at runtime, which causes a performance penalty. Now, kind of the main approaches that seem to be the most effective tend to be the architectural approaches. And the main one in that is called the NXBit. PAX is a software version of the NXBit. So the NXBit is basically a hardware change that both Intel and AMD have made to take a whole page of memory and say this is not executable. So now if the attacker adds his code to this page, then he won't be able to execute it. But these two tend to be circumvented by attackers. So we have a set of existing work, but it's not fully sufficient. So what role or how do I envision this new architecture working? Well, I made a really important claim, and I said that this architecture has to work without making any hardware changes. And yet I'm still saying that I need the processor to be able to be split across these memory spaces and have that enforced. And that's possible on Intel or AMD x86 systems by making creative use of the TLB, which is the translation look-aside buffer, and the page tables. So the TLB is a little teeny hardware cache that caches page table entries for virtual memory. By using this creative work, I can make sure that data accesses go to one portion of memory and instruction accesses go to another. So let me describe that for you. In order to illustrate it, I want to show you two quick overviews of operating systems. The first is how to handle a page fault, and the second is going to be how I've modified the general page fault algorithm to accommodate this new architecture. So if you've taken an operating systems course, you're probably familiar with a page fault, but I just want to show you virtual memory and page faults on the Intel system. So imagine that we have logical memory, and we have our 5 logical memory pages, 0 through 4. And let's say that a program is running, and it makes an access on logical page 1. Well, what that'll cause is the hardware, when it's trying to translate that to the physical frame that it corresponds to, will check the translation look-aside buffer to see if there's an entry available for logical page 1. If there's not, then that's called a TLB miss, and the hardware will then go to the page table to see if the page table has information about that mapping. If the page table doesn't have any information about that mapping, then the hardware gives up, and it signals a page fault, which is its way of telling the operating system, you're trying to make a memory access that I don't know how to do, you better fix something. So the operating system will then go to its physical memory map and will pick out a free physical frame, in this case frame 7. It'll also check its backing store, maybe the disk, to see if that page used to be in memory but was swapped out to disk to make space for something else. If it was, then it'll bring that page back in, and then most importantly, it'll update the page table to reflect that now there's a physical page backing that logical one. And at that point, it restarts the instruction. When the instruction restarts, we go back up to step 1 again, where the hardware checks the TLB, doesn't find an entry, then goes to the page table where it does now, it fills in the TLB, and it runs that instruction again at full speed. And any future accesses to that logical frame will actually go full speed because the TLB entry will be used to provide that mapping. So, how do I change the page fault algorithm so that we can have this new architecture that enforces a split between code and data? Well, in that last description, I actually told you a very small fib. And that fib is that I said that the machine has a TLB. And that's actually not true. Modern machines actually have 2 TLBs, one for instructions and one for data. And the reason for this is because they're limited in size as to how many entries these TLBs can cache, and instructions and data have drastically different usage patterns. Instructions tend to be very sequential, data tends to be more random. So to keep performance up, they have 2 TLBs so that random data accesses don't end up evicting instruction entries from that. But we can use this to our advantage. So this is what modern hardware has. Let's imagine for a moment, in a theoretical world, that it also had 2 page tables. So we had a code page table and a data page table, and the 2 were separated. Now these 2 page tables are identical except for one entry. the entry for logical page 1 in the code page table goes to physical frame 6, and in the data page table goes to physical frame 7. So that means that if we were to have these two page tables, that an instruction fetch off of that logical page would go to a different physical page than a data read or write. Now this is exactly what we're going for in trying to construct this new architecture. Instruction fetches go to one portion of memory, data reads and writes go to another. So if we could have a system like this with two TLBs and two page tables, we'd be all set. But sadly, the actual Intel machine does not have two page tables, it only has one. But what if we kept that page table invalid all the time? So whenever a TLB miss happened, the hardware would run to the page table and find nothing. So at that point, it would initiate a page fault. Now, I've made the page fault handler more intelligent. So the page fault handler is able to take that page fault and determine whether it was for a code access or a data read or write. If it's for a code access, then what it does is it goes to the code page table and it copies that entry down to the normal page table, and then it causes the hardware to initiate a fill of the TLB off of that page table, so that entry gets cached in the TLB, and then it invalidates the page table and restarts the instruction. Now, the page table may be invalid, but if there's an entry in the TLB, then the memory access will succeed, and the instruction will be able to run. And I can do the same thing for the data page table, moving those entries down and causing the hardware to load those into the data TLB. So at this point, the instruction TLB and the data TLB can be desynchronized, which means that your accesses for one particular virtual address will actually go to different physical pages, which is perfect. This is exactly what we want to have happen for our new architecture. So that's how we build this architecture in the operating system for the user level. Now there's two kind of deeply technical points that I just want to illustrate real quick about how I fill that TLB. Don't worry if you get totally lost on these two slides. They're not important for the overall vision. So how do I fill this data TLB? Well, there's actually an operation called a page table walk that I do. It's fairly simple. Within the page fault handler, I make that page table entry valid by copying the entry from the data page table, and then I touch the memory address that faulted. That causes the hardware to fill in the TLB just like I want, and then I invalidate the page table entry, and I restart the instruction, and everything continues as you would expect. To fill the code TLB, though, it's a bit more complicated. I don't have anything nice and easy like a page table walk. So I use a single stepping mode in the processor. Single stepping mode is a mode that you can set so that the processor will run one assembly instruction and then throw an interrupt for the operating system to intercede. So what I do is I make the page table entry valid by grabbing the entry from the code page table. I enable single step mode, and then I restart the instruction that faulted. So now that one instruction will run. That'll cause the instruction TLB to be filled, and then I can catch that single step interrupt, invalidate the page table entry, disable single step mode, and let the system continue to run at full speed. So how effective is this? I really ran two different types of tests. One was a benchmark test called the Weilander benchmark. And what I really want you to gather from this slide is that the Weilander benchmark was one that was designed to show all the different ways that an attacker can hijack that instruction pointer and get it to point to his injected code. But since our approach works by simply preventing him from ever executing injected code, it's able to handle all of the tests without any trouble. Now, probably the more interesting effectiveness test is on real-world vulnerabilities. So I went back and I grabbed 5 vulnerabilities from 2001 to 2003, things that covered web servers like Apache, FTP daemons, Samba, a DNS server, stuff like that, and that had a variety of different corruptible memory regions. And the goal here is to see how does the system perform on real-world attacks, and it was able to stop them all without any trouble. Now, performance. Performance is always the most important part of any sort of implementation like this. So I ran 4 different benchmarks. One was I tested the throughput of Apache, so how many pages it could serve up per minute. I tested how long it would take gzip to compress a large file, and then Unixbench and nbench are both benchmarking programs for systems. So the way to read this chart is the blue box represents an unmodified system. So it runs at what I call 100% speed. And then the purple box is the percentage of full speed that my modified user level system can run at. So my performance is above 80% in all these cases, and I consider these to be a good overall basis, or a good overall way to demonstrate the performance of the system. But I also want to show you the worst case performance of the system, because it kind of illustrates one of the main weaknesses that this approach has. So this is kind of a more zoomed in graph on how Apache, that throughput test worked. And what I found is that when I tested the throughput of Apache with very, very small pages, my performance dropped like a rock, so a little below 50%. If I tested it with really, really large pages, the performance shot up really high, almost 100%. So after a lot of digging and a lot of thinking, I figured out why this is. And it's because when you have a really, really low page size, your workload exhibits more context switching. So a context switch is when the operating system takes one running process, stops it, and lets another process run instead. Well, on a normal Intel machine, whenever you have a context switch, your entire TLB is wiped. Well, if your TLB is wiped, then that means that when the process runs again, I have to reload all of those TLB entries. And those two loading procedures that I described to you before are not fast. They're actually pretty slow. And the only reason that I get away with it at all is because the TLB caches those results. But if the TLB is getting wiped a lot, then that's going to lower performance drastically. But I want to emphasize that this is kind of the worst case results, and that's one of the reasons that I presented it. So this is kind of the user level approach. What I've just demonstrated to you is that this new architecture is effective at working at the user level. But what about the kernel level? What if there was a flaw in the operating system kernel itself that an attacker was trying to exploit? Could we protect that? The answer is yes. So if we want to do this at the kernel level, our goals are very similar to at the user level, just elevated one. So we still want to run an unmodified operating system, one that hasn't been changed at all, and we want to be able to protect it against its own flaws. Again, we don't want to make any hardware changes, and we want to ensure that the operating system itself can't circumvent the protection. So at the user level, I needed something more privileged than the application to enforce the new rules. For the operating system, I need something more privileged than the operating system to enforce the rules. So for this, I looked at what's called a virtual machine monitor. So a virtual machine monitor is just a part of virtualization, and one typical way you may have seen virtualization used is to try and run multiple operating systems on one computer all at the same time. So looking at this diagram, we have one computer, it's labeled hardware at the bottom, but I have three operating systems running on top. And the virtual machine monitor is the small layer of software that sits between the hardware and all of these operating systems. So that means that the virtual machine monitor in itself is kind of a mini operating system, but it's more privileged than the operating systems that are running on top of it. So it's there that I need to be able to enforce these rules. So what's the problem space look like with the kernel level implementation? Well, code injection at the kernel level typically manifests itself as what's called kernel rootkits. So a kernel rootkit is a program that an attacker who has root access runs that modifies the running OS kernel in memory. And usually he has the goal of hiding himself so that he can keep privileges and prevent an administrator from finding out who he is. So you may have a rootkit that would hide the listings of files, or would make it so you couldn't see that certain processes were running, or that would hide the existence of certain network connections. And it does it all in the kernel so that no matter what user level program you run to check your system, none of them will be able to find anything. Kind of our threat model for this sort of attack is an attacker who has the highest user level privileges, and most importantly, he has full memory access. So anything that the operating system can read or write, the attacker can read or write as well. And that's actually what makes rootkits so difficult to work with, is that because the attacker and the operating system have the exact same set of privileges, it's not feasible to put your prevention or your detection system at the same level, because it's just a matter of the attacker defeating it. There's a lot of previous work in this area as well. Most of it, though, is in detection. So everybody was researching rootkits, but the big question was, how can we find out that a rootkit attack has occurred? So three kind of main works that kind of illustrate this are called Copilot, State-Based Control Flow Integrity, and Patagonics. And what these three do is their entire goal is just to analyze a running system and decide if it has been infected with a rootkit. So that's interesting, and it's very good. But what we're looking for is a stronger claim of prevention, because that's what this new architecture is meant to do, is prevent these sorts of attacks. So there's really only two works that exist in the realm of prevention, and that's Livewire and SecVisor. Now, both of these use virtualization, and they're actually both going to be what I'll call complementary works to what I'm presenting here in the way that they handle preventing a rootkit attack. So techniques. What sort of techniques does a rootkit use in order to hide itself, and how does code injection play into all this? So I'm going to illustrate this with three different real-world rootkits. The first is called a DoorNG, and a DoorNG is a rootkit for the Linux operating system, and it's a kernel module. And what a kernel module is it's like a little driver, and it's loaded up into the kernel after it's booted. You know, they have drivers for things like your network card or your video card. Well, this just happens to be a really malicious driver. And what the DoorNG does is it has malicious versions of existing kernel functions, and once it's loaded, it modifies the running kernel to ensure that its malicious functions are called instead of the valid ones. So it can use this to do things like hide files, hide processes, hide network connections. Suckit is another rootkit for Linux, and it's actually very similar to Adore-ng with having those evil custom functions, but the difference is that it doesn't get loaded as a kernel module. It actually modifies kernel memory directly. It's really tricky. It's kind of a fun bit of source code to read, but it will read and write directly from kernel memory to add itself in. Now another rootkit is called foo. Foo is a device driver, much like Adore-ng, but foo targets the Windows system, and instead of having evil versions of functions, it just modifies kernel data directly. So foo's goal is if he wants to remove something from the process list, it just removes the item itself from the process list in the kernel. So it's not getting malicious code executed at the right time, it's modifying the memory image itself. Well, one thing that's very common in these three and in the other rootkits that I surveyed is that they all required new, persistent code that could be called on demand. Well, that's primed for code injection. New code that gets added to the kernel and needs to be executed later. So that's why using an architecture that's immune to code injection will make this sort of attack not work anymore. So enforcement, what do I do to build this new architecture? So actually the goal here is to run the operating system and have two separate memory spaces underneath it that the operating system doesn't know about. One is called the shadow memory, and this is where we put all of the known good authenticated kernel code. The other is the standard memory, and that's where we put everything else. And we're going to use the virtual machine monitor to manage the two and ensure that an operating system's memory access requests are routed to the proper memory space. So let me illustrate this a little bit. The top of this diagram represents the running operating system. The middle layer is that virtual machine monitor. And then at the bottom are our two separate memory spaces. So imagine that we have a system running and all of the valid kernel code's in the shadow memory and everything else is in the standard memory. So the operating system makes a memory access. Now that memory access goes into the VMM and our little enforcement module looks at it and decides what sort of access it is. If it's a guest kernel instruction fetch, so if it's fetching code to be executed by the kernel, then it shoves it down to the shadow memory, and that's where the information comes from. If it's any other kind of memory access, something for the user level programs or just a data access at the kernel, that all goes to the standard memory. So looking at this, if we were to have a system running like this with all the good code in the shadow memory and everything else in the standard memory, and we were to just run it, this would be immune to the kernel rootkit code injection. Because if the attacker manages to inject his code, it'll get written to the standard memory, but then he won't be able to fetch it from the shadow memory because it isn't there. Now an important part of this is how do we fill that shadow memory? Like that's kind of the crux of this argument is how do I get data into there and not put the attacker's data in? So the first part of that is just adding in normal kernel code. So when the system first starts up and your bootloader picks your operating system, the Linux kernel, or even just your operating system kernel in general, is thrown into standard memory. Well, at that point, the VMM intercedes, and our enforcement module reads a copy of that code and hashes it. And it compares that hash to one that it took beforehand of a known good kernel. If the hashes match, then it copies that code to the shadow memory, and then we can run our system and do the interceding, and we'll be immune to the rootkit's code injection attempts. Well, if you're anything like me, at that point you should stop and you should say, wait, it's not that simple. Sometimes there's dynamic code that gets added to the kernel after it's already started. I already described kernel modules. Well, kernel modules are dynamic code. If I add a driver to a running system, it's got to run code at the kernel level, and to what I just described, that kind of looks like injected code, because in a way it is. So how can we handle that? Well, what we want to be able to do is detect when those modules get loaded, verify that it's valid, and if it is, then we want to copy it to the shadow memory. There's a lot of pain actually in dealing with kernel modules. One is that they're dynamically relocatable, and what that means is that when the module was compiled, there were certain data structures in the kernel that the compiler didn't know where were. So he just leaves those entries blank and tells the operating system later, hey, you need to fill all these in for me. Well, that means that the hash of a kernel module will change every time you load it because those things will be filled in slightly differently. So you have to take that into account when you're doing the hashing. The other problem is that there's lots, thousands of these things, so you need to be able to handle these in an automated way. So the way that I handle them is sometime before the system starts, offline, we have all of our kernel modules. They're generated for you when you compile your kernel, or when your distributor compiles your kernel. And I run this through a profiler. And my profiler, for every kernel module, generates a profile that contains a hash of that module and a list of all of the locations in the module that could get relocated by the operating system. Now, at runtime, what happens is when a kernel module is loaded, usually it gets copied into memory, and then it's got an initialization function of some sort that gets executed. Well, after the copy has happened, because that copy will go into standard memory, but before my initialization function runs, the enforcement module will intercede, He'll read a copy of that kernel module as well as the profile, and then he'll do the hash, taking into account the relocation addresses. If they match, then he'll copy that code into the shadow memory, and everything will be able to run as you would expect. So at this point, we have a system constructed that can prevent rootkit kernel injection and can handle valid kernel modules. So improvements. There's a few problems that occur at the kernel level that didn't occur at the user level, or at least not in the same way. So at the user level, if an attacker tries to break into a process by using one of these memory errors, and I stop his attempt, usually a valid response is to just kill the running program. That's okay. It's not okay at the operating system level, because usually a good response to an attempted attack isn't shut down your machine. So for example, when you stop a kernel module rootkit on Linux, you get a screen that looks kind of like this. And this is a kernel oops, which is the kernel telling you something really bad happened. Now, the system actually continues to run, but you've lost some allocated memory that you can't get back. And just in general, it's really not clean. Windows, when you stop a kernel module type rootkit, gives you a blue screen and halts completely. Well, this is totally unacceptable, so we need to be able to handle this. Well, one simple approach is, instead of routing that instruction fetch down into the shadow memory where there's nothing, and that's what causes that, not nothing but all zeros, which cause those exceptions, what if I were to route it to a piece of my own crafted code that just says return -1? Well, the reason that I chose return -1 is because most of these rootkits are being initialized as kernel modules, and then the first thing that the operating system does is call their init function. Well, if the init function just returns -1, the operating system will assume that some error has happened, and it'll recover gracefully. So in the Windows example, instead of getting a terrible blue screen, I get a nice error message that says unable to load the driver. Well, that's nice. It's much more clean, and my system doesn't crash horribly. So that's exactly what we're looking for. It's much more elegant. So that's how the system works. The question is, how effective is it? How well does it perform? So I prototyped this in both QEMU and VirtualBox. And I implemented that kernel module profiler for Linux 2.4. So I ran all my tests on Linux 2.4, Linux 2.6, and Windows 2000 XP. So Linux 2.4 has full support. The other two operating systems have more limited support. Linux 2.6, because I didn't take the time to do the module profiling, it wasn't important for these results. And Windows 2000 XP, because I'm really not sure how its driver functionality works. So for those two operating systems, what you have to do is boot the system to a usable state and then turn on the protection. For Linux 2.4, you're protected from the moment that you start booting. So effectiveness, another really big chart. What I want you to gather from it is that I tested 24 different rootkits that span Linux 2.4, Linux 2.6, and Windows 2000 and XP, and was able to stop various types of attack vectors, was able to stop all of the rootkits without any trouble. Performance is probably a more interesting question for this. What is the performance like? So for the kernel compiling test, the performance, well, okay, I ran 4 tests. One was compiling the kernel, which required me to just compile the kernel and see how long it takes. Another was inserting a module. The question was, how long does it take to insert a module into the running kernel? And then the Apache throughput test again, and then Unix Bench, another one of those benchmarking programs. So 3 of the 4 tests ran at well above 97%, which is extremely good performance. So the blue bar represents an unmodified version of QEMU, and the purple bar represents my modified version. Now the insmod test was a little bit slower. It was down at 90%, a little above 90%. Well, as you can imagine, when you insert a module and you have to read it in and do the hashing and do the comparing and doing all of that, that actually takes a decent amount of time. So that's why you see that performance hit. But I'm not worried about it because there aren't that many workloads that involve adding and removing modules all the time, and that's all they do. So that's really not of concern. So, a summary of my work and what I'm presenting here. Most commodity systems are going to be using von Neumann architectures, and they're inherently vulnerable to code injection attacks. But it doesn't have to be that way. Not all memory architectures are. Things like the Harvard architecture are actually immune. And it's possible to construct a new architecture on top of von Neumann that's immune to that code injection problem. And at the same time, I've just demonstrated that it's usable at both the user and kernel level. It's effective and has reasonable performance. So if you have any questions, I'd love to try to answer them.
Any questions? I have one. There's one, I can still see one possible attack, or that it's not quite code injection.
Mm-hmm.
But if somehow an attacker were able to modify the relocation or the linking process of a module, could she install a fake address so that when that dynamically loaded module was executed, it would go someplace else other than where it's supposed to? Would you catch that?
So what would be the goal? Like, where would you be sending it to?
That would be the hard part, is you'd have to find some place you could send it to
In the existing code base, basically?
in the existing code base, or is there anything to prevent it from going outside of the current kernel memory? Executing outside the current kernel memory and yet still retaining kernel privileges?
Sure. So there's kind of two approaches to the attack you just described. One approach is to say, well, what if basically the attacker finds some way to get it to execute arbitrary code that already exists, and he crafts that to be something malicious. And that's an extremely valid attack, which for a long time actually wasn't too plausible until just recently, when all of a sudden there was a very good paper that described how to make that extremely plausible. So you're right, and that's an approach that I can't handle right now. It's something that we've looked at in some of our future work by trying to think about control flow integrity and such. But yes, I can't handle that particular approach. So the other one you described is another potential attack vector, which basically says, what if I were to, say, put my code somewhere else in memory, maybe in user space or something, and try to get the kernel to jump to it through some other malicious means? Well, and the important distinction is that any instruction fetch that's going to be executed at the kernel's privilege level automatically gets routed to the shadow memory. So if you install new code, no matter where you put it, you're not going to be able to fetch it. But it does raise the question of, well, what if I were to have part of my malicious code run at user level? And so that's a potential too. You could imagine this really convoluted rootkit where certain parts of the kernel code then drop to a user level privilege and run and then go back up when they're done. The problem there is, well, I do think you could construct that sort of really strange rootkit. I don't think you could do it without having to modify any existing or add any existing kernel code to help you along.
There's a problem. You need to find instructions going on within the kernel, or you need to find a sequence of bytes in the kernel which would do what you want.
Right, that's part of it. And there is work that moves along those lines, but it's still, it doesn't, you still can't construct the type of attack I just described with it.
Other questions? Well, I'd like to thank Ryan for
Thank you.
Look forward to having you all here next week. Well, I'll tell you what we have coming up, but I don't have the seminar list.
I think it's semantic next week.
Oh, yeah, we have a visitor from Spain.